Good morning. I am Ranveer Chandra. I'm at Microsoft and I serve as the CTO for Agriculture and Food. And today I will talk to you about work that I have been doing here at Microsoft for the last 7 years. Our vision is to enable data-driven agriculture and the data-driven food system. Why is this an important problem? Well, the world has a food problem. The world needs to grow more food, more than 50% more food compared to today's levels. We need to grow not just food, but good, nutritious food. And we need to grow this food without harming the environment. That is, the soils are not getting any richer. The water levels are going down. How do you grow more food, given that even the amount of arable land is not increasing? To address this problem, one of the most promising approaches is that of data-driven agriculture. That is, if you could map every farm in the world with data. For example, if you could map every farm in the world with information like this, like what is the soil moisture level 6 inches below the soil throughout the farm? What is the soil nutrient level? What's the soil pH level? If you could map the world like this, every farm like this, it would enable techniques such as precision agriculture. You could apply water only where it is needed. You could apply pesticide only where it is needed, nutrients only where it is needed. And precision agriculture has been shown to improve yields. You can take care of plants better. It has been shown to reduce costs because you use less water, you use less chemicals. It's also better for the environment for the same reasons. You're not wasting any water. You're not putting more chemicals than is necessary into the farm. The thing is, it's not just about the farm. If you look at the entire agriculture food chain, all the way from input companies to the tractor companies, to the farm, to the logistics distribution companies, to food processors, all the way to retail, to the consumer, every entity in the food supply chain would benefit if they could start using data, if they could start using AI. They would improve efficiencies. That would unlock new business models as well. But it is not just about every entity. If they could all start sharing data with one another, this could enable new business models. This could enable new productivity scenarios that did not exist before. For example, I'll just walk you through a few simple examples. If you look at traceability, food safety is one of those issues where when there is an outbreak, you want to know where that outbreak started from. You want to go back to the source. How do you enable traceability? One of the ways to do that is if every entity in the food supply chain could share data with the other stakeholders in the food supply chain. It could enable new business models such as digital agriculture, precision agriculture, where these digital advisories could get information from the tractor companies, from drone companies, from, say, the seed companies, from the farmer. You could then get much better insights about what to do when and where in the farm. Similarly, there's a lot of awareness now around sustainability. Farmers could be paid for using the right practices in the farm. However, for that, the farmer needs to share the information with other stakeholders in the food value chain. The thing is, even though the benefits of data-driven agriculture are well known, they are well established, these technologies haven't really taken off. For example, precision agriculture was first proposed back in the 80s. It's been over 30 years and the technology is still not widely prevalent. And the biggest reason is that it's just extremely hard and extremely expensive to get data from the middle of the farm. Most of these farms do not have good connectivity. You don't get good valuable data, and it is hard to drive insights when you don't have enough data from the farm. I'll talk about a few ways in which we are addressing this problem through research that we started at Microsoft called FarmBeats. The first reason existing solutions are expensive is because of connectivity. The farmer's house might have some sort of connectivity to the cloud, but the actual farm is a few miles away. Even though connectivity might exist when you plant the seeds, by the time the crops grow, the connectivity is gone. So then the question is, How will you send data from the middle of the farm, which is a few miles away, to the farmer's house when there is no connectivity in the middle of the farm? And not just data from sensors. How would you send data from drones, from tractors, from weather stations to the farmer's house? To address this problem, one of the technologies we use is a technology that I personally have been working on since 2005. This technology is what we call TV white spaces. What the TV white spaces enables is, imagine if you have a Wi-Fi router in a farmer's house or office, and you can access it a few miles away. That would be cool, right? Right now, as soon as you exit your house, your Wi-Fi disappears. And the way you can make this work is by sending Wi-Fi in empty TV channels. One of the technologies we had developed, this was back in the day, we'd written a paper which got an award at a top-tier computer science conference, was a way in which we could take a Wi-Fi signal and put them in these noisy TV channels. This is TV you watch using antennas. You know, when you browse through TV on certain channels, you get a transmission. On the other channels, all you see is white noise. With this technology, we built a way where you could put these Wi-Fi signals in noisy TV channels in a way that did not interfere with your TV reception in an adjacent channel. And the reason this is so cool is that compared to Wi-Fi in the same power, at the same power level, in UHF TV channels, your signals go 4 times farther. In VHF, they go 12 times farther, and this is in free space. Once you put them in trees, crops, canopies, your signals just keep going through. So this was a technology which we had demoed to the FCC chairman back in 2010. This was made legal in the US. Since then, we worked with multiple regulatory agencies in different parts of the world to open up the spectrum, to allow this type of communication in the TV channels. The reason this is so cool for farming is that TV towers are in cities. You have TV towers in say, Seoul. You'll have TV towers in Seattle. The farms are away from the cities. If you turn on a TV in the middle of a farm, most of the channels are just white noise. And the more noisy channels there are, the more capacity there is. So even if there are 20 TV channels that are empty in the middle of a farm, we are talking of up to half a gigabit per second of available capacity in the middle of a farm. Most recently, earlier this year, the FCC enabled new regulations in the spectrum, which allows these devices to transmit with even greater power. So you could be, until now the FCC allows in rural areas for transmitters to go up to 10 watts from 4 watts of transmission, to be mounted much higher, to allow IoT radios to communicate in the spectrum. We're extremely excited about the future of connectivity. Recently, there was a study by the USDA which said that around 70% of farmland in the US doesn't have good internet connectivity. With this, we believe one of the ways you can bring connectivity in the middle of a farm. At Microsoft, in Microsoft Research, we are exploring new ways to bring connectivity. TV white spaces is one way. We are looking at private 5G networks. We are looking at space communication, all of those, and ways to bring affordable connectivity in the middle of a farm. Because it's fundamental when you talk about the future of agriculture being data-driven, the way it can be data-driven if you can get data from the middle of a farm. The second challenge, I talked about affordability. Existing solutions are super expensive. Second question was, well, if you have to build a map like what you see on your screen here, suppose what you want to build was, say, the soil moisture level 6 inches below the soil throughout the farm. How would you build a map like this? If you wanted to build an accurate map, say for soil moisture, you would need a sensor every 10 meters. But putting a sensor every 10 meters is going to be expensive to deploy, to manage. It will come in the way of the farmer as the farmer does the day-to-day job. So the question we asked was, can you build a map like this with very few sensors in the farm? To answer this problem, to answer this question, we decided to use artificial intelligence. The way the system works is it would get data from imagery data, from drones, from satellites where you don't have drones. In fact, where drones are expensive, we came up with another way to use tethered helium balloons with cameras, smartphone mounted on it, to start getting imagery for the entire farm. So you would get this data from using satellites or drones or balloons. And then what we did is we used computer vision to build these orthomosaics. And then we use artificial intelligence to combine sensor data with aerial imagery data to build these heat maps. The technology is kind of simple to understand. That is, we intelligently place few sensors in the farm, and then we use artificial intelligence. So whenever you have a sensor and an aerial image, the corresponding pixel, we use that to train a model. And then we use that trained model to predict these values in other parts of the farm. We wrote a research paper on this where we did this for soil pH, soil moisture, soil temperature, and then we compared this to state of the art. Right now, what people do is they would put a few sensors and then you would use interpolation. Either Craiging's method is a state of the art, essentially assuming if it's a Gaussian method, if this is X, this is Y, everything in between is between X and Y, kind of assuming that. But we compared our technique of using imagery plus sensors to existing state of the art that doesn't use imagery, just uses sensors. And we showed that our scheme was 3 times more accurate in building maps like this. But of course, one of the challenges is that, yeah, we are using aerial image, say from satellites, but 77% of the Earth's images are blocked by clouds. When it is cloudy, you really can't see what's happening below the clouds, as you can see in the left part of this figure. We developed a new technology called Space Eye, using which we're able to recreate, see what's happening below the clouds, as you can see in the images on the right. And the way we build this is, again, by using AI. We use another satellite that goes around the Earth, which has synthetic aperture radar. As you know, radar signals, they go through the clouds. They reflect differently from different surfaces, whether it's metal, grass, wet soil. And we use that to then reconstruct what's happening below the clouds in satellite imagery. As you can see on the right, through the clouds, you can see when the farm is tilled, when the farm is irrigated. And this then allows us to do much more accurate models, like, for example, what I showed in the previous slide. Another challenge is the connectivity to the cloud from the farmer's house. Many farmers, they pay for broadband, but all they get is 1 to 3 megabit per second connectivity in the house. In fact, there is a farm in upstate New York where we've done deployments. Every time there is a snowstorm, there's a high likelihood that the internet connection from the farmer's house to the cloud goes off. And as I said, the connectivity is poor. You only get, say, 1 to 3 megabits per second connection. The thing is, if you fly a drone, even in a 15-minute drone flight, you could be getting over a gigabyte of data. If you have over a gigabyte of data, over a 1 to 3 megabit per second connection, it will take a very long time to send all of this data to the cloud. So then the question we asked was, if you can't send all of this data to the cloud, how do you bring benefits of computer vision, of artificial intelligence to the farmer? To address this problem, our key insight was that most farmers, they have a computer. If they have a PC, if they don't have a PC, we can ship them a PC form factor device. They can just keep this in the house. And this thing then can do a lot of compute sitting in the farmer's house. You could start doing computer vision. You could start doing AI, all of that in the farmer's house or office. Just double clicking on this, seeing what's running on this edge, on this PC, everything you see in this big gray box is running on that PC. You get data from sensors, you get data from drones, you then do orthomosaicing, that's computer vision techniques to generate a 3D point cloud. You take data from sensors, you fuse them to create these heat maps, which we then work with partners to build all of these solutions you're seeing on the rightmost column. We also get data from cameras over the TV white spaces. We can then do computer vision, and I'll talk about one of those scenarios later on as well. All of this data is lazily synced with the cloud. We've come up with intelligent algorithms. In this year's a top computing conference, we have come up with a new way to do intelligent compression, that you could be gathering data, which is a few gigabytes. How do you intelligently compress and immediately send parts of that data, which are most important, to the cloud? And this is a new technique that we've invented as well. the data is also stored on the computer. A lot of the data is stored there, and only some of that data is immediately sent to the cloud. The rest is sent to the cloud over time. We've done several deployments of this, even like from small farms to large farms, and we've tested out the technology in different types of farms. This is one of the use cases that we have with a farmer in Eastern Washington. One of the technologies that we built, this was published again in this year's SIG KDD conference, which is a top conference in artificial intelligence. What we do with this, we built a technology for microclimate forecasting. That is, once you put a sensor in the farm, we not only tell you what the sensor values are right now, we'll make predictions about what the sensor values are going to be up to 5 days in advance. And the way we do this is we took data from 50 different weather stations across Washington state. We use that to train a model. And then when you put a new sensor in the farm, we start making very hyperlocal predictions of what these values are going to be in the future. The reason this is important is that weather is one of the most important parameters that a farmer looks at when they take their farming decisions. Like, for example, the farmer in Eastern Washington, he used this data, his testimonial is on the bottom left of the slide. The farmer was looking to spray chemicals in his farm. The weather forecast said that it was going to be 42 degrees Fahrenheit. We said it was going to be 31 degrees Fahrenheit, below freezing, which is 32 degrees Fahrenheit. It was actually 30 degrees Fahrenheit. It was good that the farmer did not go and spray chemicals in the farm. Otherwise, he would have lost his crop. Similarly, the farmer, he farms 9,000 acres spread across 45 miles. Every time he takes out his tractor, he wants to know not what the wind is at the weather station, but in his farm across 9,000 acres, what is the variation of wind in different parts of the farm? He can use that, if he gets that information throughout the day, he can use it to then plan the route of his tractor. This is another use case I like talking about. This is a 4-kilometer stretch. The farmer wanted to know how his cows were doing once they were out in pasture. So we flew the drone, transmitted the data over the white spaces to an edge device sitting in the farmer's house. And within 30 minutes, we were able to flag things like from left to right, the grass is growing back well. There is a water puddle that needs to be fixed before the next planting season. The cows are pooping well, which is also important information for the farmer. This is deep learning on cow poop. This is where the cows are. This is a stray cow that needs to be herded in. All of this within 30 minutes of flying the drone. This is another use case of a farm close to Microsoft campus where we've done several demos. Bill Gates wrote about it in Gates Notes. We've shown it to several executives. We show the farmer these beautiful pictures. This is a smallholder farmer who sells his produce in the farmer's market over here and to restaurants. We show the farmer the map. For example, here on the bottom left part of the farm, we were able to flag that this part of the farm is still moist, even though we did not have a sensor over here. In this case, we were able to flag that the dark parts of the farm are still acidic. After the farmer had applied lime, we were able to flag that the dark parts of the farm are still acidic and the farmer needs to reapply lime before planting the seeds. This is another use case where we have a barn with multiple cameras streaming data over over the white spaces to an edge device. We're able to see how the cows are moving, whether a cow is sick, and be able to flag this information to the farmer. Think of this like a baby monitor for cows. So this was all in research. Then I moved over to the product side. We worked with an engineering team to help build a product around it. A product, the first version of the product, takes parts of the innovations I talked about, mostly on the AI side. Our key insight was that, well, there are many agriculture technology companies out there. Each one is building their own pipeline. They are all getting data from sensors, from drones, from tractors, all of this to the cloud. They write their own data ingestion routines, build their own applications, and each one is building something custom. What we did with FarmBeats is we said we'll make these pipelines much more efficient. So as part of the product, what we built is in the cloud, we are then ingesting data from sensors, from drones, from all of these different input types to the cloud, where once we get all of this data to the cloud, We're working with partners. So we work with drone partners, we work with sensor partners, we work with satellite companies, we work with weather partners. And with them, we try to bring in ways, we try to standardize ways in which all of this data can be ingested. Once all of this data is ingested, we work with fusing some of these using the algorithms I talked about. And then we work with partners who can then build their solutions on top. Our vision with this product is that you could specify any polygon, which could be a farm, a field, a plot. And for that polygon, we'll try to ingest as much data as possible from a variety of sources, be it from on-farm or be it from the cloud, like with satellite or weather. We bring all of that data in through partners, we work with partners, and then we fuse these different data streams so that you then become data rich. And then we work with partners who can build their ag tech solutions on top. And with this, we've announced various partnerships. Most recently, we've announced partnerships with Land O'Lakes, with the USDA, with Land O'Lakes, who's building their agriculture tech solutions on top of our product, Azure FarmBeats, with USDA ARS, the Agriculture Research Service. The researchers are using the product for a lot of their workloads to ingest large amounts of data to supplement their research. In addition to the research and the products, we're also working on building the complete end-to-end solution. That is, we also work on taking some of our innovations all the way through our CSR initiatives, our corporate social responsibility initiatives. One of the big announcements Microsoft made last year was on sustainability. Microsoft pledged to be carbon negative by 2030. That is, we'll put back more carbon than the amount of carbon that we generate. And by 2050, we are going to remove all the carbon emissions that we've generated from the time Microsoft was founded. And how do we get there? Well, part of it will come by reducing our own emissions. But for the rest, we will be purchasing carbon. We will be looking at ways to put more carbon back in soil, working with the innovators. And the reason I'm talking about that here is agriculture could be a potential way to put carbon back in soil. There's still a lot of research to be done, but this is one of the ways in which we are working with partners to see what role agriculture can be, not only in reducing the emissions of agriculture, but also helping farmers adapt with climate change and also leveraging agriculture as a potential solution to the carbon problem, to the climate change problem. In addition to that, we also work with Future Farmers of America. We built a tool, a FarmBeats kit. This kit is a way in which we are working with high schools to start training farmers while they are still in high school to start using data, to learn about artificial intelligence as part of their farming operations. We also work extensively with universities. This was work we did very recently with Purdue University, where we worked on the supply chain during COVID. We worked with Professor Jason Lusk, and we built a Power BI dashboard where you could look at any commodity across the US, be it corn, cotton, beans, and then you can see how is that commodity going to be disrupted for different counties. And you can look at what is the ag worker risk. Like in one case, we were able to flag that a meat packing plant in Yakima was going to close a week in advance before it actually closed due to COVID. Now, of course, this is all work that we're doing at Microsoft, but all of it is built with partners. Microsoft is a very partner-led company. The way we are approaching agriculture and food is that while we build the tech, the additional agriculture, the food intelligence is built by our partners. One of the things I did not mention earlier is that the reason I personally have been working in this space is because the reason I'm passionate about agriculture is that I spent a lot of time growing up in my grandparents' farm in Bihar, in India. Back then, I did not like anything to do with agriculture. The first 18 years of my life, I spent a lot of time in farms, but I did not like spending time in those farms because these villages, they did not have any electricity. They did not have any toilets. But despite that, I learned a lot about, I saw a lot of poverty growing up. I saw a lot of primitive forms of agriculture, farmers using hand-based seeding, using bullock-driven tractors. And that's been a driving force of why I have been working in this space and leading a lot of work in the agriculture space at Microsoft. And as part of that, I have been, the Farm Beats work I talked about until now works mostly for farms that are a few acres or more. But the world has over 500 million smallholder farmers who farm in 1 hectare or less, which is less than 2.5 acres. The question that we are looking to answer now is, how do you get these smallholder farmers to start using digital agriculture techniques? As part of this, I have been working with the Gates Foundation, with Stuart Collis, who's the digital agriculture lead, on just exploring what is it that's limiting the adoption of digital agriculture for smallholder farmers. We looked at this Gartner hype curve. We looked at multiple technologies and multiple digital technologies. What we saw is most of them are at the trough, are at the trough of disillusionment. We still need more work to get them over the valley, to get them to the other side. And towards that, there are multiple reasons why this is the case, including existing solutions are not affordable, affordable connectivity is not there. We need to make devices, we need to make digital agriculture solutions more usable. We need a good data sharing framework. And also we need good data sources. A lot of the data doesn't even get to the cloud. We've written a paper which will get published soon where we talk about the details. We also talk about innovation. That is, we need new technologies to help make these digital agriculture solutions more affordable. One of the technologies that I've been working on, we wrote a paper on it, was on using Wi-Fi to sense soil. This is in very early stage research, but I'm extremely bullish on the future of digital agriculture solutions. The problem here is the following. You could go buy these sensors for your farm, but these sensors right now are expensive, a few $100s, if not $1,000. For most smallholder farmers who make less than $2 a day, this is very expensive. A sensor which costs up to $1,000 is very expensive to put in the farm. But many of these farmers, they have a smartphone, even if it is an inexpensive phone. If they have a smartphone, it has a Wi-Fi chipset in it. If it has a Wi-Fi chipset in it, the key idea that we had was if you could measure the time of flight of a Wi-Fi signal, you could then use it to measure soil moisture and soil EC. That is because the time of flight of Wi-Fi depends on the permittivity of the material. If the soil is moist, it will take longer to traverse the same distance than if the soil is dry. And there are interesting challenges here about how do you make it work. We wrote a paper on this again, which won an award at a top-tier computer science conference. In fact, when we showed it to Bill Gates, he wrote a blog on Gates Notes, and the title of the blog was, "Can the Wi-Fi in your phone help feed the world?" It's still in early stage research, but I'm bullish about the future of technology where a farmer anywhere in the world can start with a smartphone, can start measuring all the things about soil, what's happening with the soil, and then start using this data with AI to start making more data-driven decisions. So as part of this study with the Gates Foundation, we looked at various technologies. If you look at each of these columns that talks about computer vision, hardware, AI, networking systems, data usability, and then looks at different technologies and their maturity levels. If you look at these slides, what you'll see is, if you look at just the first two columns, the first two rows, so sensors and satellites are more mature than other technologies that for smallholder farmers that's likely to take on first, although more work needs to be done for both of them. Another key takeaway is if you look at the second column, artificial intelligence can make any of these digital technologies much more powerful and much more effective. But one of the key challenges, if you have to look at it, is if you look at the third row, which is mostly there, a lot of more research needs to be done to enable robotics, automation, and all of that to take off in the agriculture space. So with that, thank you again for listening to my talk and for having me as a speaker at the event. I'm really looking forward to following up with many of you and working towards this vision, which I know many of you can relate to as well, to truly democratize data-driven agriculture. Thank you.